Walk into any testing center, and you will see dozens of candidates taking exams side by side. The physical reality of the room is identical for everyone, but the digital reality of what is happening on their screens is entirely different. Here is the operational paradox of the CISSP exam. Two candidates can sit down at the exact same time, answer exactly 100 questions, and experience an immediate exam shutdown. Yet one candidate receives a passing grade, while the other fails. Standard testing logic relies on volume and percentage accuracy, the assumption that a flat 70% clears the bar. The CISSP exam functions as a dynamic, algorithmic evaluation system. It operates on a mechanism known as computer adaptive testing, or CAT, which is driven by a highly calibrated psychometric scoring engine. To beat this engine, we have to deconstruct the algorithm itself. We will map the scoring mechanics, break down the hidden variables, and define an execution strategy. Understanding the mathematical architecture of the test is the first requirement for success. Look at this baseline data table. The physical parameters of the evaluation are straightforward. Candidates have a 3-hour time limit to navigate between 100 and 150 questions pulled from 8 core knowledge domains. Yet highly experienced engineers routinely fail. They walk into the testing center expecting to take a tactical, technical implementation test. The system's actual evaluation target is executive-level, risk-based decision-making. This decision tree maps the trap. Choosing to configure a specific firewall rule sits on the tactical side. Aligning your overall security architecture with organizational business risk sits on the strategic side. The exam demands judgment across broad domains like asset protection and security architecture. It does not reward command line memorization. Approaching these scenarios from a purely technical viewpoint actively triggers failure conditions within the evaluation algorithm. The CAT algorithm renders question difficulty in real time, adjusting the complexity of the next item based on every single input. This flowchart maps the algorithmic loop. The starting condition drops every candidate right here, at a central medium difficulty node. Input a correct answer, and you trigger a positive feedback loop. The system recalculates instantly and feeds you a subsequent node with a higher difficulty variable. Provide an incorrect input, and the negative feedback loop engages. The algorithm begins probing your lower competency boundaries. Through continuous adjustment, the system rapidly searches for your precise competency ceiling. Within this looping search pattern, you will encounter operational questions and pretest questions. An undisclosed number of variables injected into your exam loop are unscored noise. The algorithm uses them strictly for future calibration. These unscored variables are completely indistinguishable from the scored operational variables. Because you cannot detect the noise, you must process every single question as a high-value operational variable, capable of shifting your algorithmic trajectory. When the screen shuts down early at exactly 100 questions, the psychological shock derails many candidates. The algorithm is continuously asking a single mathematical question. What is the statistical probability this candidate exceeds the passing standard? Look at this Cartesian graph. It plots your estimated candidate ability on the y-axis against the number of questions you answer on the x-axis, all measured against this fixed passing standard threshold. The shaded band surrounding your score tracking line is the confidence interval. This represents the area of statistical variance in the engine's estimate of your ability. Each answered question acts as a sequential data point. As you provide more data, you force the confidence interval to become mathematically narrower. Termination trigger 1 is a pass. The moment your entire narrowed confidence interval rises completely above the passing standard line, the exam ends. Termination trigger 2 is a failure. The moment the interval falls entirely below the standard, leaving zero mathematical probability of recovery, the algorithm shuts off. Termination trigger 3 hits the maximum limit. If your trajectory hovers directly on the line, the algorithm requires all 150 data points to achieve statistical certainty. An early stop is never an arbitrary glitch. It is the exact chronological moment the algorithm achieves absolute statistical certainty. The official passing requirement for the CISSP is 700 out of 1,000 points, but relying on standard math is dangerous. Those 700 points do not translate to a flat 70% accuracy rate. This node visualizes psychometric scaled scoring. The difficulty tier of a specific question directly dictates its weighted point value. As difficulty increases, the mathematical weight scales up with it. Successfully navigating high-complexity judgment scenarios yields significantly more scoring mass than proving basic factual recall. This reality compounds the danger of making careless errors on foundational, lower-tier concepts. A rushed mistake immediately drops you into lower-weighted trenches. You then require exponential effort to regain access to the higher-value questions. Rushing for sheer volume destroys the scaled score. High precision on complex scenarios is the only mathematical path to securing a passing weight. The CISSP CAT is a strict mathematical filter explicitly designed to eliminate candidates relying on rote memorization. To beat it, we apply this 4-point strategic framework directly over the algorithmic loop. This allows you to deliberately optimize your inputs against the system's parameters. Point 1. Candidates must prioritize business risk and strictly align with managerial thinking. Point 2. Analyze keyword variance with precision. A single word alters the algorithm's entire contextual intent. Point 3. Select the best conceptual choice among the options, not merely a technically accurate implementation. Point 4. Focus on the architectural why rather than the operational how. Adopting this managerial mindset is a requirement before you engage with specific study materials. Now that we have mapped the engine, the next phase is mapping the distinct content within the 8 knowledge domains the algorithm pulls from. By mastering the rules of the evaluation engine first, you transition from being tested by the system to actively commanding it.